Hi everyone. In the last lecture we have seen that given a self-adjoint operator T, we can write that as a difference of two positive operators in a unique way. Now using this, actually we want to define a spectral family generated by a self-adjoint operator. Okay, so let us look at a self-adjoint operator T. So we have defined that T plus as T plus mod T by 2 and T minus as mod T minus T by 2. So we have shown that this is positive, this is also positive, and we call them as this is a positive part, this is a negative part of T, and we have shown that T can be written as T plus minus T minus, and mod T is T plus T minus, and T plus into T minus is 0, that is T minus into T plus. Okay, so these are the properties we have studied earlier. Now let us look at some more information about a self-adjoint operator. So we have defined the numerical bounds as follows. So m suffix t, that is infim of set of all inner product x with x, where x is coming from the unit sphere of H, and capital MT is supreme of inner product Tx with x, where x is coming from the unit sphere of H. Here SH is set of all x in H such that norm x equal to 1. So this is the unit sphere. The first one we call the lower numerical bound. Bound for T, and the second one is called upper numerical bound for T. This we have already discussed. Let us quickly recall the properties of these bounds. We have shown that MT times identity less than or equal to T times T less than or equal to capital MT times identity. This is one property. We have also shown that the spectrum of T is contained in the closed interval m suffix T comma capital M suffix T, and the third property that we have already shown is that these lower numerical bound and the upper numerical bound, these two are in the spectrum of T, and fourth one is norm of T is exactly maximum of modulus of M suffix T comma modulus of capital M suffix T. So these are the few information about the lower and upper numerical bounds for T when T is self-adjoint. Now let us look at, we know that spectrum of T is subset of R. So let us start with the self-adjoint operator T. Okay, and take lambda to be a real number. Let us define t suffix lambda as t minus lambda I. Okay. Then we can define t lambda plus and t lambda minus in the usual way. So let us also quickly recall. So maybe we can write as observations. When t is positive, then we can say that t plus is t plus mod t by 2. Mod t is nothing but t, so this is exactly t, and t minus is mod t minus t by 2. This is nothing but mod t is nothing but when t is positive mod, so this is 0. So if t is negative, we get in the reverse way, t plus is t plus mod t by 2. This is t minus t by 2, that is 0. When t is negative, mod t is nothing but minus t, and t minus mod t minus t, you will get this as minus t, which is a positive operator. Similarly, if you look at this lambda in R, look at t lambda plus, we can actually show that if t lambda is positive, t lambda plus is t lambda. If t lambda is negative, t lambda minus is nothing but minus t lambda. Let us prove a lemma. Let t be a self-adjoint operator and lambda is a real number. Then we can say that t lambda is nothing but t lambda plus if lambda is strictly less than the lower numerical bound of t, and it is minus of t lambda minus if lambda is bigger than or equal to the upper numerical bound of t. Let us look at the proof. First assume that lambda is strictly less than the lower numerical bound. So let us take lambda is strictly less than small m suffix t. Then we have minus lambda is bigger than minus mt. Hence we can say that t lambda is nothing but t minus lambda I, that is bigger than t minus mti. We know that t minus mti is bigger than or equal to 0 by the earlier property that we observed here, by the property 1, t minus small mti is bigger than 0. Now we know that when we have a positive operator, then its positive part is exactly the original operator. So therefore we can say that t lambda plus is exactly t lambda. So next assume that let lambda is strictly lambda is bigger than or equal to the upper numerical bound. Then we have minus lambda is less than minus of capital mt. Hence we can say that t lambda is t minus lambda I. T minus lambda is less than or equal to t minus mti. This is less than or equal to 0 because mti minus t is bigger than 0. Hence t minus mti is less than 0. For a negative operator, the positive part is minus of the negative part. So therefore we can say that t lambda plus is nothing but so in this case let us look at t lambda minus. T lambda minus is minus of the original operator. So or we can say that T lambda is minus of T lambda minus. Okay, so this proves the lemma in both cases. Now we want to define the spectral family generated by a self-adjoint operator. Let us look at the definition. Let T be a self-adjoint bounded operator. Then the spectral family generated by T is a family of projections E lambda, where lambda is coming from R, where E lambda is exactly projection onto null space of T lambda plus. So this family of projections we call as the spectral family generated by T. Let us look at a simple example. Suppose we have, so here null space of T lambda plus is again mod T lambda plus T lambda by 2, where T lambda is nothing but T minus lambda I. Okay, so let us look at a simple example. Let us take P to be an orthogonal projection. On a Hilbert space. Then we can write P as 0 0 0 identity, this identity on the range of the projection. So this decomposition with respect to null space of P and range space of P. Okay, now let us take lambda to be a real number. Then we have P lambda, that is P minus lambda I, this is minus lambda I, this identity on the corresponding space 0 0 1 minus lambda I. So this identity is on the null space of P, this identity on the range of P. Okay, now we want to look at what is P lambda plus. So P lambda plus is nothing but P lambda plus mod P lambda by 2. So mod P lambda is nothing but this is lambda mod lambda 0 0 mod 1 minus lambda identity on range of P, this identity on null space of P. Okay, hence we can say that this is nothing but mod lambda minus lambda by 2 identity on null space of P 0 0, and this one is 1 minus lambda plus mod 1 minus lambda by 2 identity on range of P. Okay, so this we can get depending on lambda positive or negative, we can actually get these things. When lambda is negative, so lambda is less than 0 implies p lambda plus we get as mod lambda is nothing but minus lambda, so this is minus lambda identity. So when lambda is less than 0, 1 minus lambda is positive, so you will get 1 minus lambda. Okay, so null space of p lambda plus is nothing but 0 space, hence we can say that E lambda is nothing but projection onto this null space of p lambda plus. So this is 0 whenever lambda is less than 0. So when lambda 0 less than lambda less than 1, this implies p lambda plus okay. When p lambda is when lambda is bigger than 0, you will get p lambda to p lambda plus. So if you look at this part star, and lambda is bigger than 0, so mod lambda is nothing but lambda, so you will get the first one to be 0. So p lambda is 0 0 0, and when lambda is less than 1, 1 minus lambda is bigger than 0, you will get the last entry to be 1 minus lambda. This is null space of p, this is range space of, this is into this identity, this is 1 minus lambda identity and range of p. This is what p lambda we get in this case. So E lambda is projection onto null space of p lambda plus. So this is null space of p lambda plus is this part 0, that is null space of p only. So this is projection onto null space of p. You will get this as I minus p, and if lambda is bigger than 1, we can actually show that when lambda is bigger than 1, by star, the first entry 1 1 entry you get 0, second entry also you will get 0. So in the so p lambda plus you will get 0 0 0 0. This is with respect to null space of p, range of p, this is null space of p and range of p. So in this case p lambda is 0, p lambda plus is 0, that means E lambda is projection onto, so range of null space of E lambda plus, null space of p lambda plus, but null space of p lambda plus is the full space, this projection onto the full space, this is identity. So in conclusion, we can say that E lambda we get 0 when lambda less than 0, you will get I minus p between 0 less than or equal to lambda less than 1, and identity when lambda bigger than or equal to 1. So this is a spectral family generated by an orthogonal projection. So let us look at some important properties of spectral family generated by a self-adjoint operator. So let us write as lemma. Let T be a self-adjoint operator and E lambda be the spectral family generated by T. Then we can say that E lambda is a 0 operator if lambda is strictly less than empty, and identity if lambda is bigger than or equal to the upper numerical bound. Okay, so let us look at the proof. We know that when lambda is strictly less than empty, so if lambda is strictly less than empty, then we have shown that T lambda plus is T lambda by lemma 1 T lambda and T lambda plus are same when lambda less than empty, and when lambda bigger than or equal to capital MT, that is minus of T lambda minus. So we can say that whenever lambda less than empty, T lambda plus is T lambda. So in this case it is positive, and we also know that when lambda strictly less than small mt, then T minus lambda is invertible, because spectrum of T contained in the closed interval small mt comma capital MT. So as lambda less than mt, so we have T lambda inverse exists and it is bounded. Hence we can say that null space of T lambda plus and that equal to null space of T lambda in this case, which is 0. Hence E lambda in this case is projection onto null space of T lambda plus. This is projection onto a 0 space. This is 0 operator. Okay. On the other hand, if lambda bigger than or equal to capital MT, then we know that T lambda is minus of T lambda minus. So we want to look at spectral projection, spectral family generated by T. Hence, so we want to look at what is null space of T lambda plus. So in this case T lambda is nothing but minus T lambda minus. So we have, but T lambda is nothing but T lambda plus minus T lambda minus, that we got as minus of T lambda minus, or we can say that T lambda plus is a 0 operator. Hence we can say that null space of T lambda plus is null space of the 0 operator, that is nothing but full space. Therefore E lambda is nothing but projection onto null space of lambda plus, that is projection onto the space H. This is identity. So we have shown that whenever lambda is bigger than or equal to the upper numerical bound of T, then E lambda is identity operator. Okay, so this completes the proof of this lemma. Let us look at one more important property of this projections, family of projections. So let us write as lemma 3. Let T be a self-adjoint operator and E lambda in R be the spectral family generated by T. Then we can say that E lambda commutes with every operator that commutes with T. So E lambda commutes with A for all lambda in R whenever A commutes with T. Okay, so to show this, actually we know that E lambdas are orthogonal projections. So if a projection commute with an operator, that is nothing but the range of the projection must be a reducing subspace. So to show that E lambda commutes with A, so it is enough to show that range of E lambda, that is null space of T lambda plus, is a reducing subspace for A. So let us take A to be the bounded operator such that AT equal to TA. We want to show that range of E lambda, that is null space of T lambda plus, reduces A. Okay. So AT equal to TA implies A T lambda equal to T lambda A, because T lambda is nothing but T minus lambda I. But if we know that if an operator commutes with another operator T, then the first operator commutes with its modulus also. So from this we can say that A commutes with mod T lambda. It's a property of the square root of an operator. So this actually implies from these two we can say that A commutes with T lambda plus. So let me call this as equation 1. We know that A commutes with T lambda as well as mod T lambda, hence we can say that A commutes with their average, that is A commutes with T lambda plus. Now first we want to show that null space of T lambda is invariant under A. Let us take X is in null space of T lambda plus, then we have T lambda plus AX is nothing but A T lambda plus X by 1, and we know that T lambda plus X is 0 because X is coming from null space of T lambda. So we have taken X is in null space of T lambda plus, and we have shown that T lambda plus AX is 0. That means AX is in null space of T lambda plus. So therefore we can say that A of null space of T lambda plus is contained in null space of T lambda plus. So null space of T lambda plus is invariant under A, that is range of E lambda is invariant. Now we also want to show that it is a reducing subspace. So it is enough to show that range of E lambda is invariant under A star. So by 1 we can actually show that A star T lambda plus is T lambda A star. Let us, because T lambda is a positive, T lambda plus is a positive operator, taking adjoint both sides for the equation 1, we will arrive to this equation 2. Now following the same method as we have done earlier, so we can easily show that null space of T lambda plus is invariant under A star. So null space of T lambda plus is invariant under both A and A star. From that we can conclude that null space of T lambda plus is a reducing subspace for A. So therefore which concludes the proof. That means E lambda A equal to A E lambda. Okay. Now using this observation, using this lemma, we can actually conclude many things. The first one is, now E lambda commute with every operator that commute with T. Now we know that T commutes with itself, so T must commute with, so that means E lambda should commute with T. E lambda T equal to T E lambda for every lambda in R. Now from this we can actually show that E lambda commutes with T lambda for every lambda in R. Now E lambda commutes with T lambda. Now we also know that if you take E mu, where mu is real number, E mu commutes with T and E lambda commutes with T. From that we can conclude that E lambda E mu is E mu E lambda for every lambda mu in R. Now let us look at T lambda E lambda. This is T lambda, we can write as T lambda plus minus T lambda minus multiplied by projection onto null space of T lambda plus. This is T lambda plus multiplied by projection onto null space of T lambda plus minus T lambda minus into projection onto null space of T lambda plus. Now whenever we take x in null space of T lambda plus, the first element will be T lambda plus on x. So we can say that whenever for x in H, T lambda E lambda x is T lambda plus projection onto null space of T lambda x minus T lambda minus projection onto null space of T lambda x. Now whenever we take, so this we can write as minus of T lambda minus projection onto null space of T lambda plus x. Okay. Now this we can write as minus of T lambda minus I minus projection onto null space of T lambda plus perp. We can write this is nothing but minus of T lambda minus x minus projection onto null space of T lambda plus is perp is nothing but projection onto range of T lambda plus closure, but this is minus of T lambda minus x minus, you can write this as minus of T lambda minus x plus T lambda minus multiplied by projection onto range of T lambda plus is nothing but projection onto null space of T lambda minus x. So this follows because T lambda plus into T lambda minus is T lambda minus into T lambda plus. This is zero operator. So range of T lambda plus is contained in null space of T lambda minus. So its closure is also contained in null space of T lambda minus, but the second operator become 0. So hence we can say that this is minus of T lambda minus x. So therefore we can conclude that T lambda into E lambda, so minus of T lambda minus. Now if you look at T lambda into I minus E lambda is nothing but T lambda minus T lambda E lambda, but T lambda E lambda is nothing but minus T lambda. So this is T lambda plus T lambda minus, but this is nothing but T lambda plus minus T lambda minus plus T lambda plus minus. So this you will get T lambda plus. So the conclusion is that T lambda into I minus E lambda, that is T lambda plus, and in fact we can show that this is also equal to I minus E lambda into T lambda. So this is the conclusion. But when we look at T lambda into E lambda, you will get that is minus of T lambda. Okay, so these are some of the observations that the spectral family generated by T satisfy. So in the next lecture we will be looking at some more important observations about the spectral family generated by T, and we also want to obtain T as integration over the spectrum of T with respect to this spectral family generated by T. So that we will be looking at in the next class. Thank you very much.